Graphs of rational functions. A rational function r is a function that can be written in the form r of x equals p of x over q of x, where p and q are non-zero polynomials and the power of q is greater than or equal to 1. In effect, a rational function is the quotient of two polynomials. That is, take a polynomial and divide it by a polynomial, and you have a rational function. The simplest rational function is the reciprocal function, 1 over x. The reciprocal function is the quotient of a 0-degree polynomial p of x equals 1 and the first-degree polynomial q of x equals x. It doesn't get simpler than this. Let's have a quick review of this function. The reciprocal function is given by f of x equals 1 over x. Because division by 0 is undefined, the number 0 is not in the domain. In set notation, we write the domain of f is all x that belongs to the set of real numbers minus 0. To determine the range takes some thought. Let's play with this idea. F of 3 equals 1/3 and f of 1/3 equals 3. F of 1/5 equals 5 and f of 5 equals 1/5. F of negative 8 equals negative 1 over 8 and f of negative 1 over 8 equals negative 8. In general, the reciprocal function has an interesting property. F of a equals 1 over a implies that f of 1 over a equals a. F of x equals 1 over x, f of a equals 1 over a, f of 1 over a equals 1 over 1 over a, f of 1 over a equals 1 times a, which equals a. Recall from algebra, the function f has a hole at x equals k for all values of k where q of k equals 0 and p of k equals 0. Provided the multiplicity of the factor x minus k in the numerator is greater than or equal to the multiplicity of the factor x minus k in the denominator. Otherwise, there will be a vertical asymptote at x equals k, as evidenced in the example of function g to the left. A rational function has a vertical asymptote x equals k for all values of k where q of k equals 0 and p of k does not equal 0. Many imagine that all rational functions have domain restrictions that manifest as vertical asymptotes or removable discontinuities. This is a misconception. Let's take a look at two examples of rational functions that have no domain restrictions at all. Here we have f of x equals 1 over x squared plus 1, and here we have 4x over x squared plus 1. The domain of f and g above is the set of real numbers. Both are rational functions, neither have domain restrictions. There are no vertical asymptotes or holes. Finding the range of a rational function is usually a bigger challenge than finding the domain. There are some strategies to try. Let's consider a few. To begin, there are some easy to explain cases. R of x equals k over ax plus b, where k does not equal 0. The domain is all real numbers except for negative b over a. The range will be all real numbers except for 0. Find the domain and range of r of x equals 1 over 2x plus 5. The function r is a transformation of the reciprocal function. The implied transformation is 1 over 2x plus 5 equals 1/2 times 1 over x plus 2.5, which means the range is unchanged. The domain is going to be all real numbers except for negative 5 over 2, and the range is going to be all real numbers except for 0. Here's another approach to help find a horizontal asymptote if one exists. Recall from algebra how to find a horizontal asymptote, or HA. If the degree of the numerator is greater than the degree of the denominator, there is no HA. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is y equals 0. If the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is the ratio of the leading coefficient of the numerator over the leading coefficient of the denominator. Given a rational function r in the form r of x equals p of x over q of x, the x-intercepts of r are those real values z where p of z equals 0 and q of z does not equal 0. The y-intercept of r is the ratio given by p of 0 over q of 0, provided that q of 0 does not equal 0. Note, not all rational functions have intercepts, and some have x-intercepts but no y-intercept and vice versa. What are the x and y intercepts of each of the functions? All right, so the x-intercepts are going to be when this whole thing equals 0, and that will take place when the numerator equals 0, but the denominator does not equal 0. So 3x squared minus 3 equals 0, 3x squared equals 3, x squared equals 1, x equals positive or negative 1. Now, if we put positive 1 in here, then that would be 6. If we put negative 1 in here, then that would be 2. So both of these work, which means our x-intercepts are at 1, 0 and negative 1, 0. For the y-intercept, that's when we plug 0 in for x. So that's 0 and that's 0. Therefore, the y-intercept will be negative 3 over 4. So we'll have a point at 0, negative 3 over 4. You always have to test these x-intercepts, by the way, because if that x value also makes the denominator 0, that means that it's undefined at that point. There will not be an x-intercept. So here, we set 3x plus 12 equal to 0. We're solving for the x-intercept. 3x equals negative 12. X equals negative 4. So that means there might be an x-intercept at negative 4, 0. However, if we plug negative 4 into x, we get 0 on the bottom, which means that there is not actually an x-intercept there. And then for the y-intercept, we plug in 0 for x, and we get 12 over 8, which is 3 over 2. Therefore, there is a y-intercept at 0, 3 over 2. Finally, down here, we have 5x squared plus 5 equals 0. 5x squared equals negative 5. X squared equals negative 1. There is no value for x that you could plug in here that would equal negative 1 because it's squared. Therefore, there is no x-intercept. For the y-intercept, we plug in 0 for x, and we get 5 over 1, which is 5. So there is a y-intercept at 0, 5. And here are the answers. Given a rational function f where the power of p of x is greater than or equal to the power of q of x, f of x equals p of x over q of x, which equals q of x plus r over q of x. There is an asymptote y equals q of x, where q of x is the quotient of the division of p of x by q of x. Perform the indicated long division to determine q of x and r. Here we have two polynomials, one divided by the other. We can use synthetic division, and we get 1x plus 7 plus 12 over x minus 1. This is our remainder. The graph will be asymptotic to q of x. See the next slide. The line q of x equals x plus 7 is called a slant asymptote. To the left and to the right, the graph of f of x will get closer and closer to q of x. Perform the indicated long division to determine q of x and r. Here we have this polynomial divided by this polynomial. We can use synthetic division, and we get q of x equal to x squared plus 2x minus 4, and the remainder is negative 2 over x plus 1. The graph of f will be asymptotic to q. See next slide. The curve q of x equals x squared plus 2x minus 4 is called a parabolic asymptote. To the left and to the right, the graph of f of x will get closer and closer to q of x.
Let's now turn our attention to a form of rational functions where the power of the numerator is less than the power of the denominator, and the denominator can be expressed as the product of linear factors. The goal here is to show that the rational expression can be split up into what is known as partial fractions. Here's an example. Find the constants a and b to make the following a true statement. 4 over x squared minus 1 is equal to a over x minus 1 plus b over x plus 1. To begin solving this equation, we need to multiply both sides of the equation by the least common denominator. The denominator of the rational expression on the left-hand side of our equation factors in to be x plus 1 times x minus 1. Since the denominators on the right both contain at least one of these factor expressions, our LCD will be x squared minus 1, which is equal to x plus 1 times x minus 1. So we're going to begin by multiplying both sides by x squared minus 1. And we can clearly see that on the left-hand side, they cancel each other out. And again, I'm going to rewrite this as x plus 1 times x minus 1 on the right to help us with rationalizing. Let's first multiply our LCD by our first fraction. When we do so, we will get a times x plus 1 times x minus 1 over x minus 1. Notice that the x minus 1's cancel out, and what we're left with is a times x plus 1, which is what we have here. If we use the same idea with our b term, meaning we multiply x plus 1 times x minus 1 by b over x plus 1, we end up getting b times x plus 1 times x minus 1 over x plus 1. And in this one, the x plus 1's cancel out, so we're left with b times x minus 1. The next thing that we can do is distribute the a to both terms in the first set of parentheses and getting ax plus a. We can also distribute b to both terms in the second set of parentheses and get bx minus b. And then, using the commutative property, we can rewrite this expression as ax plus bx plus a minus b. And if you'll remember, the commutative property of addition says that you can add numbers or terms in any order, so therefore we can take these two and switch them around. And notice when we do that, both of these first two terms have an x in them, so we can factor that x out, and we're left with a plus b, that quantity times x, plus a minus b. Now we have a major idea here. If some number a times x plus some number is, say, 5x plus 2, then a would equal 5 and b would equal 2. So in general, if you have an ax plus b, and that's equal to the same thing with capitals, then you can say that little a is equal to capital A and b is equal to capital B. So using this concept, we actually have a coefficient and a constant over here. And so far on the left-hand side, we only have a constant. We don't have a term that has a coefficient. So therefore, we can add a 0x here and then have a plus 4 and have that be equal to a plus b, that quantity times x, plus the quantity a minus b. Well, now using the fact that the coefficients are going to be the same, we can write that a plus b is equal to 0, and we can write that a minus b will equal our constant term of 4. So we have one equation, again, a plus b equals 0, and a minus b equals 4. Oh wait, this is a system of linear equations. And if you'll recall from Algebra 1, we can solve a system of linear equations using either substitution or elimination, or graphing. Elimination seems to be the easiest option, so let's add these two, mainly because I have a plus b and a minus b, and I know that they're going to cancel out. So when I do that and I add straight down, I will have a plus a, or 2a. And then if I add straight down here, 0 plus 4 gives me 4. So I have 2a is equal to 4. If I divide both sides by 2, I get that a is equal to 2. So that's how we get this value in our first fraction that's shown in the solution. And then, if I was to use either equation from my system, either the first equation or the second equation, I can use it to solve for b. I'll use the first one because it seems a little easier. We know that a is 2, so I can fill that in, plus b is equal to 0. And then if I subtract 2 from both sides, I get that b is equal to negative 2. Hence why I have a minus 2 right here. So that's how we have our b value. Therefore, our final answer in this problem is f of x is equal to 4 over x squared minus 1, which is equal to 2 over x minus 1 minus 2 over x plus 1. Let's try another example. F of x is equal to 1 over x squared plus x, which is equal to a over x plus b over x plus 1. To begin solving this equation, we need to multiply both sides by our least common denominator. Well, the one on the left can be factored to become x times x plus 1. And notice each of our factors on the right contain at least one of these factors. So this is going to be our LCD. So we're going to multiply both sides of our equation by this LCD. X times x plus 1 and x times x plus 1. When we do this on the left-hand side, both of these cancel out with the entire denominator over here, so we're left with 1. And then on the other side, we're going to have a times x plus 1 over x plus b times x plus 1 over x plus 1. Notice that the x's in our first expression cancel out, and in our second one, the x plus 1's cancel each other out. So therefore, we can rewrite this as 1 is equal to a times x plus 1 plus b times x. Now we can distribute the a to both terms in the parentheses, and when doing so, we would get a times x plus a plus bx is equal to 1. And then using the commutative property, we can switch this a and this bx around to write it as ax plus bx plus a is equal to 1. We can also add a 0x to the front of this, because 0 times anything is 0, and we do have terms that contain an x here. So let's drop this down. 0x plus 1 is equal to, let's factor that x out of these two terms, and when doing so, we get a plus b times x plus a, and now we have two expressions that are equivalent to one another, and we can use them to construct a system of equations. Our first one, this coefficient, 0, is equal to a plus b. So let's write that down. 0 is equal to a plus b. And then our constant of 1 is equal to plus a. So we know that a is equal to 1. Well, since we already know that a is equal to 1, that is one of the values that we need here, we can then substitute a into the second equation in our system to have that 1 plus b is equal to 0. And if I subtract 1 from both sides, the value of b will be negative 1. So therefore, we can rewrite our equation as f of x is equal to 1 over x squared plus x, and that is equal to a is 1 over x, and then plus b is negative 1. So instead of writing plus negative 1, I can just write a minus sign here, and then 1 over x plus 1. And that is the answer to this question. This slide verifies that the solution that we found as 1 over x squared plus x is equal to 1 over x minus 1 over x plus 1 is correct, where a is 1 and our b value is -1.